Thanks for the organization of everything. So I'll just start with some reminders of what we did last time. So we were interested in the K-stability of Fano varieties. So we had our X was a smooth, complex, projective manifold, variety, I guess. Variety. And yeah, so in this talk, we're not going to be really talking about anything non-singular, and we won't really worry about continuous automorphisms. And so we were looking at the Fano case, so where minus kx is ample. And so we had formulated this notion of K-stability in purely divisorial terms. So we use this delta invariant. We can also use this beta invariant, to recall. It's something that acts on the divisorial valuation. So I'm going to pick valuation u, is the order of vanishing along some divisor lying above x, and the beta invariant of nu is this log discrepancy function that Yuxia introduced, acting on nu, minus 1 over the volume of minus kx to the power of n, and we had this sort of indefinite integral that converges, where we just pick, we integrate the volume of minus kx minus lambda e. So e is the divisor defining valuation. And so we have this whole collection of results, which we can basically summarize as those Li Shu, Li, Jita, Blum Shu, many others, but the result stated that basically x minus kx is k-stable if and only if this beta invariant is positive on divisorial valuations. And in fact, so I think this is this initial part, it suffices to consider valuations that are finitely iterated. So let me just introduce some notation. They're usually called dreamy. So nu is dreamy if nu is some divisorial valuation. And so as you shall explain, there's this correspondence between filtrations and test configuration and test configurations, but also valuations. And filtration has a graded algebra. And so nu is finitely iterated as well, in the sense that the filtration associated to nu is finitely iterated. Here actually suffices to check dream evaluations. So in this lecture, we're going to look at K-stability for general polarizations. We're no longer going to assume that X is Fano, but we're just going to look at an arbitrary ample line bundle. And in the first part, I guess we're going to look at how to extend just this formalism and its results in this general polarization case and see what happens. So this is the notion of valuative stability. Which was studied by Dervan Legendre. And was also building on some earlier results of Fujita. So we're going to pick X as a forward. And we're going to pick L a polarization, so L and ample line bundle on X. And strictly speaking, so we're going to talk about notions such as openness. So we can also allow irrational polarizations, but simplify matters, we're just going to talk about actual line bundles. L is possibly irrational. So again, as Yusha explains, K-stability traditionally is defined in terms of Boucksom-Jonsson invariant, which is something that has an entropy part, and then there is an energy twisted by Ricci part and an energy part. And so to define the beta invariant in a way that coincides with this Boucksom-Jonsson invariant for general polarizations, we need to introduce additional terms in this. So we're going to pick, as before, new some divisorial evaluation. We're going to assume that C is just 1 for simplicity. And so we can define beta of nu, and I'm going to take into account polarization here, which we'll measure later. It's again the log discrepancy evaluated at nu. Then we add some cosmological constant, which is n times minus kx. It's minus 1 over n. It's kind of a derivative of the volume in a sense, or the volume of L. We again have this integral that we had before. So the volume of L minus lambda E d lambda, and a slightly uglier term. So again, 1 over the volume of L times the integral of the derivative at 0 of the volume of L minus lambda E in the direction of kx plus tkx. So I differentiate this at 0 with respect to t, and I integrate with respect to lambda. So here, just noting that I use the facts, so it's a result due to Boucksom-Jonsson, and also Lars Statsa. That's the volume function is actually C1 on the ample, and in fact on the big cone of X. So is C1 on big X. So this derivative at 0 absolutely makes sense. So we have defined this, and then we can just extend our notions of K-stability. Okay. We're going to say that XL is valuatively semi-stable if this beta invariant is non-negative on all dream evaluations. So new dreamy. So again, for all finitely generated and divisorial valuations. And we're going to say that it is relatively stable if this, in a sense, is coercive. So if beta of nu is larger than epsilon times what we call the expected vanishing order, which is this part here. So SL nu, just 1 over volume times this integral minus lambda d lambda, which you can see kind of as it acts kind of like a norm on the space of valuations. And so it's relatively stable if it is coercive in a sense with respect to this norm. This is true for all new dreamy. So just a little remark. So traditionally, this would correspond more to uniform K-stability, and in the Van-Legendre paper, in fact, they call this valuatively uniformly stable, but to keep similar terminology for divisorial stability, which we'll see later, I think I'll just call this valuatively stable for now. Relatively stable corresponds. This looks like the traditional notion of uniform K-stability. Uniform stability. And so the first main result, so we would like ideally to have something like this. So the main result of the Van-Legendre is that XL is valuatively stable if and only if it is uniformly K-stable with respect to test configurations with irreducible central fiber. If and only if XL is uniformly K-stable. So again, in the sense of this Jonsson-Stacking invariance on test configurations. With irreducible central fiber. So it's expected in a sense. So we had from last time, there was this correspondence between dreamy evaluations and these test configurations, irreducible central fiber. Of course, the results, I mean, there are many things to prove. It's not so easy to just say that, but it is expected in a sense. And so what we see from this is that basically, so this class of valuations is insufficient for testing the full extent of K-stability. Say, stability. This thing that was very nice in the Fano case is that we could restrict to checking only exclusively on this finitely iterated dreamy evaluations, but in the general ample case, it's not sufficient. You can't expect to have all these nice fine iteration results. So in a sense, we need to test against a larger class. The silver lining is that this notion is still quite nice. So we have these results due to Liu, 28, 23. saying that valuative stability is an open condition on the ample cone. So if XL is relatively stable, then XM is going to also be relatively stable if M and L close enough on the ample cone. This is an open condition. On the ample cone. These openness results are quite big, important results. And it seems that the fact that we could possibly prove some type of openness as well for more general K-stability if we're able to extend it correctly and to test against larger class of evaluations. So yeah, no, I mean, it's most of the biggest results in the field are proving by iteration of some minimizer or something. It's
but it's known to be
in which setting? I'm not sure.
Yeah,
what's
so
your question?
You could have a valuative stability criterion where it requires the test on many things or the test on all.
Divisorial. Yeah.
So,
No.
but in the minus kx case.
Yeah. So that was what you shall explain last time, that you can, I mean, you can turn this beta invariant into a delta invariant and just computing the minimizer of some functional, and the minimizer is finely iterated. Yeah, no, it's yeah, no, of course, it's a big thing. So what are we looking for really? So last time also we introduced this Boucksom-Jonsson operator. It's Non-Archimedean Boucksom-Jonsson operator. So if we have XL, it is configuration. And it's not irreducible. The central fiber is some sum of divisors. And E. Then we could associate to it this measure MAXL, which was living on this Berkowitz space, so this compactification of the space of divisorial evaluations, which is a compact space. It's very nice to use. And this one pair measure is just 1 over the volume of L. So this is the test configuration for XL. The sum of this BE, L restricted to E to the power of N. And this is the coefficient of the Dirac mass at the divisorial evaluation at E. So for this Gauss extension and the section of this map, we could see this as an actual divisorial evaluation on X. And basically, so we can see this is potentially up to rescaling. This is a convex combination of these Dirac masses at divisorial points. So we can naively define a class. So we're going to define them as divisorial measures. So it's just going to be a finite convex combination. Dirac masses. At divisorial evaluations. So let me call their sets like mdiv. So this set mdiv naively, so naturally it contains all these valuations from before, because to divisorial valuation you can just associate the direct mass at. It also contains, in a very strong sense, the set of test configurations. So let me just recall this notion of equivalence of test configurations first. So we say that XL prime or prime are equivalent if so we can dominate both of them. There exists an X prime prime, which lies above them. This is a rational morphism. And, it has to be unique if it exists, such that the pullbacks, so I call this by 2, this by 1. The pullbacks of the polarizations also agree on this common pullback. So by 1 star L equals the 2 star of prime. So they, from a K-stability point of view and so on, they encode the same data if they are equivalent. So we don't really care about quotienting by its equivalence. And in fact, the important point is that this Monge-Ampère operator is actually going to descend to an injection up to this notion of equivalence. Let me just claim this as a fact. The Monge-Ampère operator descends equivalent injection, sorry, from this TZ, which last time we denoted as the set of all test configurations. We modeled by this equivalence relation here, and it actually embeds into the set of divisorial measures. Technically, we also modeled by some rescaling action, but this doesn't really matter for this talk. And as we'll see later, we can put a metric on both of these sites, and this will in fact be an embedding with dense image. So we'll see later. We can metrize the right-hand side, and this will be an embedding with dense image. So this is a class that is not much bigger in a sense than test configurations and contains all of them. And the very nice thing about it is that it's also independent of the polarization. So this is just a set of measures at points on Berkeley space, supported on these divisorial points, which are completely independent of L. And so they contain densely this set of test configurations, which could a priori depend on L. So it's actually very good to test for K-stability, especially from the perspective of openness. So this mdiv is in a sense the optimal set that contains all test configurations and does not depend on our L. So it would be great if we could, for example, extend this beta invariant to this class, and it's actually what we can do, albeit at the expense of a lot of Berkovich formalism, which I'll get into now. So, yes. So it's the set of test configurations as an abstract set. And then you have this equivalence relation on test configurations. You just take the quotient by this.
Are we implicitly fixing XL?
I'm sorry.
Implicitly fixing variable X, variable L.
Mm-hmm.
Okay.
Mm-hmm. Yeah, I can. If it's more clear, I can write Excel. And the point is that this MDiv actually doesn't depend on this information. So unfortunately, you have to get a bit more in depth about filtrations. So basically, what I'm going to try to do now is to explain how we can purely formally rewrite this beta invariant that we had before as a purely Berkovich expression that really lends itself to being generalized to this larger class MDiv. Right, so it's going to be a a long definition. So we are looking at filtrations F of the section ring. Section ring RL, which is the sum of these RMs. This is just the space of sections. No. But we don't want any old filtration. Actually, for example, if we look at the dimension function, so we fix M, we're going to look at filtration such that the function which to lambda associates the dimension of this filtration at lambda of the mth grade piece is going to look essentially like this. So it is going to be piecewise continuous and piecewise constant and left continuous, decreasing, and it's going to be 0 for an element high enough to the right, and it's going to be equal to the dimension if we pick lambda small enough. And this is going to be continuous. So in technical Bourbaki terms, I guess this means that F is exhaustive, which means that we catch the whole dimension separated. It means that we go to 0, left continuous, and non-increasing. And we're also going to ask for filtration to be graded. So it has to respect the structure of a section ring. If I pick F lambda Rm, then I multiply through the map magnification of sections through with F mu Rn, going to be included in F lambda plus mu Rm plus n, and bounded, which means that there exists a uniform constant such that for all m, F minus C times m equals Rm, and F C times m equals 0. Which means that this gap between the first jump and the last jump is going to grow at most linearly. And so, yes.
So is lambda
Lambda is a real number. So we have a collection of vector spaces of subspaces of our graded piece, which has to behave kind of nicely and in this way. And these points at which the dimension jumps, they're called the jumping numbers of the filtration. And they contain quite a lot of information about it, actually. So these are the jumping numbers. I'm going to call lambda I m indexed by I. And the important thing is that these jumping numbers, which contain almost all of the information we really need about the filtration, they're going to equidistribute. So what we can do is we can define a measure I'm going to call sigma m of f, which is going to be a distributional derivative of this volume function. So it's going to be a sum of direct masses at these jumping numbers. It'll be minus d dt. We just have some normalization, m minus x, dimension of f, m lambda rm, which really means it's going to be a sum of direct masses at these normalized jumping numbers, lambda m over m. So these. And the theorem due to Boucksom-Jonsson states that these measures actually converge weakly to a quality supported measure. And the m of f converge weakly against continuous functions to a compactly supported probability measures for I'm going to call sigma of f. And in fact, we can also express it in this kind of distributional way. It's going to be the derivative in the sense of distributions of truncated version of the algebra of sections of the volume of that variety are greater than t, or are greater than t. Its mth piece is just the filtration at mt or m. By Boucksom-Jonsson, these actually have a positive volume. Yes. And this is going to be very useful in giving kind of a variational expression for these beta invariants. Are any questions for this filtration stuff? Yes.
What's in the first m to the power of 1 to the dimension of x, and then
The dimension. Yeah. So it's just renormalizing this volume function that we have here. I could be a lambda, sorry. Yes, it's a lambda. Yeah, no. Yes. Yeah, it's the derivative respect to lambda in this expression. Sorry? No, it's a distributional derivative. So this, in the sense that ddt f against the function is the integral of minus the integral of f against g prime. It's in this distributional sense, in the weak sense.
so we end up
So it's a measure. You can see it as a linear functional acting on functions in that sense. And yeah, if you do the computation in this case, if you have a piecewise constant function, it's just a sum of direct masses. But yeah, you can just use this direct mass version if you prefer. Yes. So then the thing is that to a continuous function on our vector space X on, we can associate a filtration as well. So if phi is continuous on X on, then we can define a filtration. Oh, sorry, something I didn't mention is that we can use this to define the volume of filtration. So we define the volume F to be just simply the first moment of this measure. It's the integral over R of lambda d sigma of F. So it's a way to centralize the notion of volume, classically. If you take the trivial filtration. And through this, so we're going to be able to define the volume of a function. So we define a filtration at phi, where at phi lambda of Rm, which is the set of solutions in Rm, such that nearest m phi of nu. So phi is a function on X on, so X on is space of valuations. So this phi acts on valuations is greater than lambda. And you can actually check that this defines a filtration in that sense here. Let me call this space such filtrations live in FR, and they're just what I'm going to call filtrations for now on, because everything that we're going to see is like this. And this is indeed such a filtration. So now we can also define the volume of a continuous function, taking into account polarization. So the volume of a continuous function phi is just L phi, which is the volume of F phi, which is so the first moment of sigma. So this actually depends on the polarization, although phi does not, because we associate to phi first a filtration on the section ring of L, and so then taking this volume necessarily requires taking L into account. So for example, so this has nothing to do with continuous functions, but just if F is induced by evaluation as before, which is divisorial, then the volume of F nu is exactly this expected vanishing order, which was this integral 0 to infinity of L minus dE dt. So you can see it, for example, using this distributional expression here, because it's proof. So full of F nu, it's just the integral of volume of this truncated algebra with respect to T. But this in graded piece M is just the filtration of new M lambda MT, I guess, or M, which is the set of S such that your order of vanishing of S E is greater than MT. This is exactly the algebra observations of this. Yes.
So in the definition of the equation of lambda
Mm-hmm.
this definition depends on
It depends on. Oh, sorry. Yeah. So this is this phi is defined on x on. So this is just for all new in x on, which is a space of evaluations. Yes. Yes. Yeah. Indeed.
The non-Archimedean stuff is supposed to be some sort of limit of
Yeah. So
some sort of a limit.
well, you can see it as the in the case that this induces a test configuration, for example. So when this is finally generated, this captures the volume of the test configuration that you get, for example. But this is also a much more general object than this. So now we can introduce this sort of variational expression of this SL invariant. So we can define so if nu is just any measure on x on, any say radon measure something, we can define the norm of mu is L, and it's going to be defined as a supremum over all continuous functions in x on of the volume of phi against the integral of phi against mu, which if you squint hard enough, you can sort of see as a Legendre transform in a sense. And now my claim, which yes, I don't have the time to prove seriously, is that this beta invariant I had before, so which was this ax of nu plus some plus this SL plus this kind of ugly derivative term. Can actually be expressed as the integral of this log discrepancy function against delta nu, this is trivial, plus the derivative at 0 of this norm in the direction of kx, mu L plus T kx. And the upshot is that this is actually something, so D is delta nu in this case, is that this is something that a priori at least seems to make sense for divisorial evaluations, divisorial measures as well. Just roughly, so to see, yeah, and we have this and this norm delta nu is exactly SL of nu. So to see this, basically we use literal variational arguments to show that this sub is computed by, say, a function phi with phi vanishing at our evaluation, and the volume of psi equals the volume of this filtration. And then because of this kind of example here, this is exactly SL mu. I get that I'm not really proving anything seriously here, but what I'm saying is that so this norm part that is going to be useful in defining actually relative stability can indeed be expressed as the SL that we know and love. And to show that this part corresponds with this part, it's more or less kind of a derivative under the integral calculation, although you can't really differentiate, so you have to use Lipschitz estimates. But you can take my word that this actually works. And now the point is that this is very possible to extend to these real measures as well. SL is this expected vanishing order, which is this integral. There is also a volume. And I'll make a favor myself. The point is that you can compute this kind of dual energy of a measure in the evaluation case as exactly this invariant, which we saw to work as a norm already in the evaluation case. Right, so now this claim here actually allows us to extend beta to mdiv itself. So this is just purely formal, but then this derivative would make no sense in terms of pure intersection theory, for example. So the entropy part is just going to be the integral of the star discrepancy function against the mu. So we saw that this was well-defined. This function was well-defined on divisorial valuations, and you could extend it to the whole space. So it makes sense as a function, but this is just going to be sum of direct masses at divisorial points. So this is fine. And for the derivative of the energy parts, probably the energy parts uses deep results. That's this norm, which generalizes this expected vanishing order, is also differentiable on the input cone. The norm function having fixed mu, which to L in the input cone associates the norm of mu with respect to L is C1. This is much harder to prove because you don't really have this nice integral expression for the norm, so you can't really try to differentiate under the integral and so on. So you need to rely on some quite deep Holder estimates. It's basically doing pure potential theory, but on the Berkeley space, which is the strength of this machinery, if you can bear the slightly expensive technology. But ultimately, this is all based on free, non-Archimedean free potential estimates, which are basically flowing from the Hodge index theorem, as everything boils down to generalized intersection numbers. And I guess I'll just finish by introducing the basic definitions. Journal chase. Okay. So we can define the beta invariant for mu divisorial. Beta of mu is the integral of ax d mu plus the derivative as equals 0 in the direction of ax of the norm of mu. What's the ax? Exactly this expression that we had before, except that we allow Montreal measures. And we say that xl is divisorially stable. Yes, divisorially semi-stable first. If this generalized beta invariant is non-negative on MDiv and divisorially stable if beta of mu is coercive with respect to this norm on MDiv. I guess it'd be nice to keep track of the indices as well. And let me just state the main results in the spirit of this Van der Schaande result that we had before. So XL is divisorially stable. If and only if XL is uniformly K-stable for filtrations, which by which I mean filtrations in the sense as before, these graded, bounded, nice filtrations. So of course I still haven't defined properly this K-stability for filtrations thing, because we defined Boucksom-Jonsson invariant for test configurations, but general filtrations are not very nice geometrically, at least. And this is slightly more surprising as well, because we don't have any sort of an isomorphism between or an embedding between these filtrations and MDiv. In fact, these are rather strictly contained, so it's a bit more surprising that we get something more general for testing as a smaller class, but we'll sort of, I hope, make sense of this in the next lecture. I think I'll stop here. Sure, yeah.
Just make sure I understand correctly. Everything here is still in the case when X is the Fano, even if we're not necessarily taking the end.
No. X is arbitrary.
Oh, so everything. Okay.
So this, I'm taking an ample L, so X is just protective.
Right, but X is up to.
Yeah.
In both of your definition of like divisorial, unstable, and valuative,
Mhm.
you also have a mention for projectability.
I mean, we don't really take into account. I mean, we don't really think about continuous morphisms, for example. I mean, yeah. Like a non-discrete morphism group, for example. I suppose you could define it. You need to. You probably need to reduce this norm, for example. I mean, there's no theory for that, but yeah. Yeah. Yeah.
No, a different question.
Mm.
So, assuming we're in the setting of the discrete element,
Mhm.
stability of Fano.
So I mean, this is your paper with Theo, more or less, right? You can test against equivariant stuff. And... Yeah. Hmm.
Can I ask kind of a big question, which is that
The best questions.
the point you've been advertising is that the space of divisorial measures is dependent on volume.
Mhm.
So one can ask for a kind of quantized version of this, where you're trying to do variation of GIT. You want, I mean, is this somehow related to the fact that the one parameter subgroups you test against are independent of the polarization? Or, I mean,
No, so a way to see it is that where is the we'll talk about this in next lecture, but this MDiv is isomorphic to a class of filtration for subclass we're going to call divisorial filtrations. And this is going to depend on L, but this isomorphism is going to be also depending on L, but this does not depend on L. So you just if you test the beta invariant in this sense, then it amounts to testing against a changing class, but you don't see the value change as you do it, and it's a completely formal isomorphism as well. The Calabi-L theorem.
and I mean, in the space of test configurations, you've got this picture where it's a kind of limit of divisible limits or something.
Mm-hmm.
Is there some version of that on the divisorial measure?
Again, I think only through this. I mean, the only way that I could see that is through this isomorphism again, where you see these filtrations as elements in the boundary. Yeah, I mean, yeah. Mhm. To another bundle, you mean? Yeah, yeah. So that's the point of the story, is that in this picture, the entropy part, which is usually the hard part to control, doesn't vary at all, and it's much easier to control these energies and their derivatives. Like they have these strong Holder estimates to control them. Like it's not easy, but it's much easier than the entropy parts. So we do have quite a lot of control over what happens as you vary.
I also have a really big question.